Suppose you come to class one day and you find you're having a pop quiz. The quiz has 4 multiple choice questions. You have had no time to prepare for this quiz, so you are completely guessing for each of these questions. There are a total of 5 choices, one of which is correct for each question. I'm going to let you digest this for a minute. It could be a bit startling. I'm sure this has all happened to us at one point in time. And my ultimate question for you, this is the setup, is what is the probability that you get 3 questions correct? So in a sense, you might pass the quiz, 3 of 4 questions correct. So I have a little setup here so that we can keep what we're about to talk about organized, where we're going to talk about this test or quiz experience. So let's say you get the first one correct. So there's a 1 in 5 chance that can happen. Remember, there are 5 choices, one of which is correct. Question 2 rolls around. Guessing, you get the second one correct. Third question, you get correct. And then, of course, we only want 3 questions correct, so the 4th question is incorrect. So we want to figure out the probability. We've talked about them as individual questions, but collectively, what's the probability of this particular thing occurring? Well, each question is independent of the next, so we're going to be able to multiply these together using the multiplication rule back in chapter 5. So that's a total of 4 out of 625. Now, that's not a very likely thing to happen, 4 out of 625. But there is a little hope here, if you'll follow me. I call this case 1 because there are a couple other ways that you could get 3 questions correct and 1 question incorrect. So in this first case, the 4th question was incorrect. There could be a circumstance where you get the 3rd question incorrect and the remaining questions correct. We'll multiply those together as well, and the probability is again 4 over 625. Probably can see where I'm going with this. In case 3, the 2nd question is incorrect, the rest of them are correct, same probability. And finally, case 4. So your chances of getting 3 correct answers by guessing has improved just a little bit. So if we add these together, these 4 possible ways this could happen, we get a collective 16 over 625. If we divide that out, that's about 0.0256. So for me, a 2.56 chance doesn't sound very good. I might want to study for the pop quizzes. Guessing doesn't seem to be a good strategy. So you might be a little overwhelmed at this point, having to sit and think this out, or wondering how you might do this yourself without a teacher guiding you. Well, there is help. The binomial model is to the rescue. And you may see this model at this moment and think, that's not any better. Well, actually, it is a bit better. It's a way of finding these probabilities where the formula does a lot of work for you. You don't have to think as hard as you would in the first circumstance or way I showed you. So the assumptions for the binomial model, how are we going to know that we can even use this model? Well, the assumptions for the binomial model in general are that there are 2 possible outcomes. We call them success and failure. The probability of a success is constant. There are a fixed number of trials, and the trials are independent. So let me apply this a little bit to what we just did. We have 2 possible outcomes for each question. You get it correct or incorrect. The probability of getting it correct, that's our success, I would assume, is constant. And that's why I had to emphasize that you were guessing on every single question. So there's always a 1 in 5 chance you could possibly get it right. There are a fixed number of trials. Trials here are my questions. So this is a quiz with a set number of questions, not an open-ended number of questions. And finally, the trials are independent, or the questions themselves are independent of one another. So whether you get the first one right or wrong will in no way influence whether you get any of the other questions right or wrong. So this is a perfect situation for a binomial. So in order to make this equation before work, you have to identify a few things in order to do what we're going to see and plug and chug the variables in. So what does N mean, P, X, Q? Well, N is the number of trials. P is the probability of a success. The letter Q in this equation or this formula is the probability of a failure. And X is the number of successes. So we want to go back and use this formula. In our example, N is 4. That is 4 questions, which relates back to 4 trials. The probability of success, that is getting the question correct, is 1 over 5. Q, the probability of a failure, is that 4 in 5 chance that you get it incorrect. And finally, X being the number of successes, well, for this probability request, we want to know what's the probability we get exactly 3 questions correct. So X is equal to 3. Now follow me here. Just kind of put these things we just defined on the last slide here, color-coded them, and I just simply put them into that equation that you saw. And so after everything is in there, the first thing I want to do now is simplify this slowly. Oh, before I do, I probably should explain what that exclamation point is doing in our formula. This is called a factorial. It's in factorial. The exclamation point is spoken as factorial. And basically what it does is you take the number before the exclamation point and you multiply it by every possible whole number less than it. So for example here, if we had 6 factorial, that simply means 6 times 5 times 4 times 3 times 2 times 1, which if you multiply all those numbers together, 6 factorial equals 720. It's a bit of shorthand for a field of mathematics called combinatorics. So here we have it. We want to see this. This is that formula again, just a wee bit smaller. So I want to first clean up the subtraction. So a couple of subtractions there, so that's all that's going to change here. And now, on this next step, I want to expand the factorials. In other words, take the exclamation points out and put in what they mean. So you can see here the 4 exclamation point in the numerator, 1 exclamation point, and it's just 1, and 3 exclamation point. Still working slowly. If I divide out that fraction there, multiply the numerator and denominator and divide it out, you can do this on your own if you have trouble following me. That is 4. That number is 4 out front now. I don't know if you can see my mouse here. I'm circling it. That number is 4. And of course we have the 1/3 or 1/5 to the 3rd power and the 4/5 to the 1st power. So what this has just done is recreate what we did initially. Think about it. There were 4 scenarios that we had, or cases I should say. I called them case 1, 2, 3, 4. So this thing with all the exclamation points is called a combination. It counts the number of possible cases you'll have. And of course, we have the 1/5 and 4/5. They look familiar. And these are just exponents. So if I expand them out, you can see here 4 times 1 over 5 times 1 over 5. So this looks a lot like what we had in the earlier way of solving. We had 4 cases where there were 3 1/5ths and a single 4/5. In other words, 3 correct answers in green and 1 incorrect answer in red. So I'm going to go ahead and multiply this out, and we get the exact same probability we got from doing it in a more sort of cumbersome kind of way, where we just kind of thought it all out. This formula will lead you to the correct answer, and it's a little more streamlined than just casing everything out. So where we eventually end up with this is that if we have a formula, as you can see before, a lot of plug and chug here, computers are really great at making this process go yet even faster than what we see here on the screen, because they can take the numbers you've identified and do these computations at lightning speed. So we're going to end up using technology, the one we choose for our class is StatCrunch, to ultimately solve these problems for us.